Hello. Hi, so welcome to another seminar in our seminar series, and today we have Professor Emily Levesque from University of Washington here with us, and she's going to talk about the weirdest stars in the universe. So like I said, Emily is a professor nowadays at Washington. She did her PhD at University of Hawaii, and then she had Hubble fellowships and so forth. She's active in the massive star research community, where she does a lot of work on, for example, red supergiants and also the objects she's going to talk about today, of course, among other things. And Emily is actually also very active and renowned in the educational world in terms of being an educator and also public speaker and that. And it was quite funny because I asked her before now, so how's your book coming? And then her reply was immediately, which one? So that tells you a little bit. And actually turns out, I didn't know that. I was talking about her public science book, but she has also actually now published, a more of a research-oriented book on red supergiants, and now she's also coming out with a textbook on stellar physics on a graduate level, so check these out. And then she has also written The Last Stargazers, about how modern astronomy, this is a public science book, and about how essentially observational astronomy is transforming from, basically all observers going to the telescope to doing more and more remote observing, something which we're very familiar with at this institute, for example. So feel free to check that out and talk to Emily about that. But now I give the floor to her, and she's going to talk about the weirdest stars in the universe, exploring the evolution of Thorne-Zytkow objects.
All right, thank you very much. It sounds like the microphone is now working. Excellent. So good morning, everyone. I'm so glad to have the chance to visit and speak here. I'm especially excited because I know it's a room full of experts on stars. I apologize in advance. I got off an airplane from the States last night with a 1-year-old. So if there are any slightly incoherent bits of the talk, this is part of an explanation for why. But what I'll be talking about is research that I've been doing over the past year as part of my sabbatical and lead-up research before that on Thorne-Zytkow objects. I usually like to start these talks with the reminder of what Thorne-Zytkow objects are, because even within the stellar physics and massive star evolution community, they're oddities. So Thorne-Zytkow objects were predicted by Kip Thorne and Anna Zytkow back in the mid-1970s. They were basically imagining an other or sort of alternative stellar structures that could outwardly appear like normal stars, but work a bit oddly in their interiors. What they imagined was a neutron star functioning as the core of a massive stellar envelope that can actually be supported through a combination of gravitational accretion and nucleosynthesis in the envelope. So you wind up with this big diffuse envelope that outwardly looks like a regular star, in this case a very cold star, but the core is a neutron star instead. There's a very fun animation showing how we imagined, at least initially, a Thorne-Zytkow object could form. So in the animation, you start with 2 blue supergiants in a binary. The more massive of the 2 will complete its evolution first. It'll start to get to the end of its life. It'll quickly undergo core collapse, throw out the supernova. I love that the camera shakes when the supernova hits it. What you're left behind with is a blue supergiant and neutron star binary. When the blue supergiant then expands into a red supergiant, it engulfs the neutron star, which spirals in through a conveniently not illustrated process, because that's still a big question mark in how Thorne-Zytkow objects form. And we're left with a Thorne-Zytkow object, or a TZO, the easiest way to abbreviate them. So the general picture, if you were to step through each step of the binary evolution, is what we just saw. There are several question marks in how accurate we think this picture of how to make a Thorne-Zytkow object is, and I will come back to them later. Once you've skipped past the how does it form process, and you then look at how a TZO should appear, there's a few traits that we're able to base a search for TZOs on. We know that a neutron star supporting a big envelope like that should appear from the outside as a very cool and luminous star. It should lie at, or it should even lie beyond, the Hayashi limit on the HR diagram for massive stars. So it should be hovering in about this region of the HR diagram, similar to where red supergiants are, possibly even colder. As a direct consequence of that, given how luminous it is and how big and extended the envelope is, we think it should also be very strongly mass losing as a result. Again, similar to a really luminous, pretty evolved red supergiant. We think possibly that Thorne-Zytkow objects should be more common at lower metallicity. This is still really speculative, but it comes back to those pictures of how binaries could form a TZO. The idea there is that if you have two binaries, two stars in a binary, having them closer should quickly be the easiest way to form a TZO, and close binaries are easier to form at lower metallicity, where those big line-driven winds in the stars are a little bit weaker. Finally, the aspect of a TZO that we were most interested in when we started studying them was that they should have a very unique chemical profile. If you picture a cross-section of a regular red supergiant, you have the cool surface of the star, the helium-fusing core, and big convective regions in the middle. If we then turn this into a Thorne-Zytkow object instead, there's two really key differences. You now have a neutron star core instead, and we think that the envelopes of these stars should be the very most extreme version of an envelope in a red supergiant. You have enormous convective cells that directly connect the bottom of the envelope near the neutron star core to the surface. The convection speeds in these stars are also incredibly fast. We know even in red supergiants that you can get supersonic convection speeds. You wind up with shocks in the interior of the stellar atmosphere. We think something should be going on that's very similar in TZOs. But it also leads to the potential for some really odd nucleosynthesis processes. The one that is most notable is something shortened to the IRP process, but that stands for the interrupted rapid proton process. And the idea is that you have a packet of material in the stellar envelope that gets dragged down to this region at the base of the envelope near the neutron star core. The temperature is very high, the density is very high. You wind up with protons getting very rapidly pushed onto the nuclei of the atoms in that packet of material. So each atom sort of starts sprinting up the periodic table. Before it can reach a stable endpoint of that process, though, that packet of material gets dragged back out into the outer layers of the star, and those elements start to undergo beta decay. Again, before they can hit a stable endpoint of beta decay, they're dragged back down to the core, and the whole process begins again. So you get this interrupted rapid bombardment of protons onto these atoms, interrupted by spates of beta decay. This was modeled exhaustively in a paper by Cannon back in 1992, and then refined a couple of times since then. But it gives you abundances of things like molybdenum or rubidium or ruthenium, and the abundance profile itself is what sticks out as unusual. You can get rubidium through things like the S process, but the full profile of this should be very unique to the IRP process and not easily mistaken for the S process or binary pollution or some other thing that could contribute to odd abundances on the surface of a red supergiant. So this gives us one set of elements that we can look for. There's a couple others that are interesting too. You should actually build up an excess of lithium in the atmosphere of a TZO for a kind of similar reason. You have this very rapid convection going on between the cooler surface and the hotter base of the envelope. So in a case like that, you wind up with very efficient beryllium destruction and a lot more time for lithium to survive in these sort of cooler outer layers. So you build up an excess of lithium at the surface of these stars, which in the case of a red supergiant should appear as at least somewhat unusual. There's ways to build up excess lithium in the atmospheres of red giants. With red supergiants, we know less about this, but it is a bit harder to explain. And then finally, the actual act of making the Thorne-Zytkow object itself should leave behind a chemical fingerprint. When that neutron star merges with the core of a main sequence star or a red supergiant or similar, the animation sort of depicted it as, oh, the neutron star disappears and magic happens and it becomes the new core. In reality, it's much messier. As far as we can understand, the neutron star, as it approaches the helium core, will quickly disrupt classic helium fusion and will lead to a sort of chemical chaos moment as the neutron star becomes the new core and disrupts and disperses the fusion core. Chris Tout and colleagues modeled this back in 2014, and they figured out that one byproduct of this would be excesses of things like calcium. So you could wind up looking for a calcium excess in a red supergiant 2 or other elements that specifically come from this merger. So put together as a profile, this should be a chemical signature that you would only expect in a Thorne-Zytkow object as opposed to just S-process enhancements or the odd lithium enhancement or a one-off event that could be caused in other red supergiants or a very luminous red giant. So backing up and looking at all of this, we would look for a Thorne-Zytkow object by looking for something very red supergiant-like, especially luminous, especially cold, with this strange abundance signature. It sounds like a fairly straightforward search to do, but for a very long time, people searching for Thorne-Zytkow objects would check a single strange star, or they would pick a single element and search for it in red giants or red supergiants. And the overall search had not gone anywhere because the observations were actually very challenging. If you look at the spectrum of a red supergiant, it's dominated by these big, broad absorption bands of titanium oxide. You actually can't even see the continuum of this star at all. It's been completely blanketed out by the titanium oxide bands. One of the papers on Thorne-Zytkow objects back in the early 90s specifically focused on where, in this mess of an optical spectrum, you could even try looking for some of the IRP process products that you would need to identify a TZO. The Cannon 1992 paper has pages of element abundances and every single line and every single signature you could possibly look for. This paper abbreviated it down to a much shorter list of lines that might not be completely buried inside a molecular absorption band. So this starts to give you an observational recipe for where to look for lines of a Thorne-Zytkow object. Even this one isn't perfect because all of these bluer lines, the yttrium line, the ruthenium line, are in a region of the red supergiant spectrum where your signal to noise is often really bad. These stars are so red and so bright in the red that with most standard spectrographs, by the time you've got enough signal in the blue to search for a line like this, you've saturated the red and really lost a lot of the key information that gives you things like the star's temperature or some of the other diagnostic lines that you want to use. Another reminder when we're talking about red supergiants as opposed to cooler or lower mass M stars is exactly what that spectrum means as we start to look at cooler and cooler stars. What I've plotted here is one of the Mark's stellar atmosphere models for a red supergiant, and it's adopting a spectral type here of K1, so a very early K supergiant, and a temperature at the surface of 4,000 Kelvin. If you cool that down, you can quickly see what happens to the spectrum. Those titanium oxide bands appear, form, they get immensely strong. They blanket out the continuum even faster than you would expect it to drop as the star cools, period. And you wind up with the very coolest stars having very little sort of free continuum left to search for IRP process products. This process, this idea of basing red supergiant temperatures on these big broad absorption features is how I started working on red supergiants. It was actually my very first research project as an undergraduate summer student working with Philip Massey at Lowell Observatory. We used these titanium oxide bands to build an effective temperature scale for red supergiants, basically finding that these could be used as really effective thermometers, measuring effective temperatures in these stars in the Milky Way. Our next step after the Milky Way was to then look at red supergiants in other galaxies in the local universe. We looked at red supergiants in the LMC and SMC, in other local dwarf galaxies within the local group, and we started determining a lot of red supergiant temperatures and a lot of red supergiant spectral types. An interesting thing that had been previously observed that we then confirmed with these big samples was the trend toward earlier spectral subtypes as a function of metallicity in these galaxies. You can see that the average spectral type of a red supergiant moves from about M2 in the Milky Way all the way down to K0, K1 in WLM, which has about 20%, 10 to 20% the metallicity of the Milky Way. There's two reasons for this. One is that you're going to be basing spectral type on the effective temperature of the star, you're also basing it on the sheer amount of titanium and oxygen that are available, which is going to go down at low metallicity. You would probably expect that this would be enough to completely explain that trend of spectral type, that as you go to lower metallicities, you simply have less titanium and oxygen, so a star with the exact same temperature is going to have a much earlier spectral type than it will in a higher metallicity galaxy because the lines are simply weaker. But there's a second detail in here that actually becomes really important for searching for Thorne-Zytkow objects and how we got started on this project, because the stars themselves actually do get warmer as a function of metallicity because of how the Hayashi limit moves. What I've done in this plot on the right is zoomed in on 3 sets of evolutionary tracks from the Geneva group. So the Milky Way is shown in black, the LMC is shown in red, the SMC is shown in blue, and you can see this nice clear march of the Hayashi limit to warmer and warmer temperatures. We hit about 3600 Kelvin in the Milky Way, that then goes up to 3800 Kelvin in the LMC, and 4200 Kelvin in the SMC. So this effect just comes, it's just an opacity effect. It comes from there being more free electrons at higher metallicity. You get a higher abundance of ionized hydrogen. This is the main opacity source in cool stars, and there's this massive dependence on, temperature to the 9th power. So you wind up with this actual shift in how cold stars are allowed to be while still remaining in hydrostatic equilibrium. So when you go back and look at this histogram, what you're starting to see is what should be a rule saying as you go to lower and lower metallicities, red supergiants should not be allowed to exist past a temperature of 4200 Kelvin, apparently in the SMC, or a spectral type of mid to late K, supposedly. There's a few outliers, especially as you go to the lowest metallicities, that seem like these stars shouldn't be allowed to exist in those galaxies. You have stars that are too cold to stay in equilibrium for the SMC, for WLM, for NGC 6822. These stars leapt out at us as being unusual, and when we observed them, they actually caught our attention as these kind of strange variables. They go through periods where they are too cold for their host galaxy, and then when we went back and observed them again, at the time we were just fixing a mistake in our observations, and we happened to get, time-resolved spectroscopy. When we observed them again, they had gotten hotter and wound up lying on the correct side of the Hayashi limit, but also being brighter, being dustier, and being more luminous. When we observed them repeatedly, we saw them jumping back and forth over the Hayashi limit. So they struck us as these strange variable stars. We thought we might be seeing sort of existing opacity effects in the star's atmosphere coming from their mass loss. We published a paper on these weird too cold stars in the Magellanic Clouds and thought that was the end of it. And then Phil Massey and I got an email from Anna Zytkow that started off with, years ago, Kip Thorne and I invented theoretical models of stars. And when an email starts like that, you immediately sit up and listen. She went on to describe what Thorne-Zytkow objects were, why they thought that they might look like extra cold and extra luminous supergiants, why they might be expected to appear preferentially at low metallicity. And she ended the email with, let me know if there may be some interest in pursuing these lines of inquiry. And we wrote back saying, yeah, these sound fascinating. We have only ever observed these stars with low resolution spectra. We should go look at them with an Eschel spectrograph to see if we are seeing any signs of a TZO. So we put in a proposal to Magellan. I am still a little surprised that they gave us time to go search dozens of red supergiants, saying, hey, one of them might be these weird theoretical stars that nobody's found for 40 years, but they did. And across the normal red supergiant spectrum, there were several regions of interest we decided to zoom in on. We specifically looked at the rubidium, lithium, and molybdenum lines that Beale 1994 paper had highlighted that should be easily observable in a red supergiant atmosphere. Now, the spectra here that are zoomed in are 3 spectra of a normal red supergiant. And we originally thought that this was going to be the whole goal of the paper, because we don't have a good picture of how much molybdenum in that one tiny line blended with an iron line. We don't know what a normal molybdenum line looks like in a small Magellanic Cloud red supergiant. Lithium is still not entirely well understood in red supergiant atmospheres. Rubidium is complicated by also being enhanced by the S process, but as a group, we figured we would get a bunch of spectra of normal red supergiants, establish a baseline composition for molybdenum, for rubidium, and call that it. And then say, if you want to look for a Thorne-Zytkow object, here is the basis to look for. You might want something that shows an excess in all three of these lines. As we took our observations, though, one of the stars in our sample, which was Harvard variable 2112, came out with a spectrum like this. So again, this is a normal red supergiant spectrum. This was the spectrum of HV 2112. I can back up and show it again, but you can watch how all three of these lines get dramatically stronger. The lithium line is now much stronger than any of its neighbors. The rubidium line and its ratio to the neighboring nickel and iron lines is much stronger. And that molybdenum line, you would never think that was impressive if you'd only seen this spectrum, but compared to the last one, the ratio with the neighboring blended iron line is much, much bigger. This star had met the criteria that we had set out, saying if something is a Thorne-Zytkow object, we need to see enhancements of this suite of elements that can't on their own be explained by any other stellar interior. So we immediately started paying attention to HV 2112. The way these observations worked was that we went to Magellan, got the data, and about a year and a half later, I was finally sitting down in front of the spectra, measuring abundances or measuring line ratios of these individual lines. When I got to HV 2112, I remembered something that had happened during the observing run itself, because we were getting our data with the Mike Eshel spectrograph. We were observing with Nydia Morel, who is an expert at Magellan and an expert on Mike, and she was reading the raw data as it came in. And when the raw spectrum of Mike came out, you can barely see it with the contrast here, but we basically have lines and lines of shell absorption, and you can see these tiny little bright fuzzy dots. It doesn't look that much better on the actual image. It's barely readable. But Nydia looked at this nearly blank, nearly impenetrable screen and immediately says, I don't know what that is, but I know that I like it. Because she had noticed these weird emission lines, which you normally don't expect to see in a red supergiant spectrum. We got low resolution spectra of these stars as well, so that we could fit those titanium oxide bands and measure temperatures at the same time as we were getting our high resolution data. And if you look at the low resolution spectrum of HV 2112, here are those lines. You're actually seeing strong hydrogen emission in a very weird line ratio scenario. You don't have a Balmer increment here, you actually have a Balmer decrement, and H delta is the strongest emission line. Usually this spectrum just strikes everybody as bizarre. If anybody has worked on Myra variables and looked at Myra spectra, this jumps out as familiar because you see similar emission features in the atmospheres of Myras that are thought to be driven by non-LTE effects when you get sort of pulsations in the outer layers. This was apparently also happening in the atmosphere of HV 2112. Nydia had noticed those emission lines in the raw data. Months later, when I was looking at the line ratios, the star jumped out at us as a potential Thorne-Zytkow object, and it was only then that we realized the two stars were the same. That in addition to having the abundances we would expect for a TZO, this star was also clearly doing something very strange in its outer atmosphere, and we were seeing very weird signs of pulsations. Finally, when we put it on the HR diagram, I showed this before, where we would expect TZOs to be in the same region as red supergiants, perhaps a little bit cooler. HV 2112 is sitting in the exact part of the HR diagram where we would expect to see a TZO. These were all really exciting signs that this could be a Thorne-Zytkow object, but we stopped short of declaring it a Thorne-Zytkow object. We actually had a journal tell us, we will publish your paper if you say you've discovered a new type of star. And we wrote back saying, we can't say that. This is a candidate. There's other ways to explain odd abundances. There's other ways to explain those pulsations. There's other red supergiants we know that look apparently too cold for their environment, and we don't think it's being caused by a neutron star core. We have to establish it as a candidate for now, but it's the strongest candidate that anyone has found yet for a Thorne-Zytkow object. Work on this star then went on for a few years. We were trying to solve other problems regarding red supergiants. We had PhD students working with us on related topics, and it took a few years before we fully turned our attention back to TZOs. The way that that started was actually at the American Astronomical Society summer meeting in 2021. I was giving a plenary talk at that AAS, and as part of the talk, I was invited to organize what they call a meeting in a meeting, so sort of a miniature day-and-a-half long meeting as part of AAS, taking advantage of all the attendees being in the same place. I was allowed to pick whatever topic I wanted, and I said, we're doing a whole meeting on Thorne-Zytkow objects. There's a small handful of people who are working on these or topics related to this, and we're all going to get them into the same room. The catch was this was the summer of 2021, so this was deep in the midst of COVID, and it was a remote meeting, so everything was done over Zoom. The perk of that was that we could have attendees from all over the world, so we managed to definitively observe one type of Thorne-Zytkow object because we got Kip and Anna to join and give the opening and closing talks. But we also had experts on binary evolution, on common envelope evolution, on weird quasi-stars, on gravitational waves. So we were able to combine everybody that had been working on TZOs or related topics and spend a day and a half saying, how can we prove whether or not we found one? If we have found a TZO, what should we do with it? If we haven't, how should we keep looking to see whether these stars truly are real? What are the current questions related to Thorne-Zytkow objects? And there are many current questions related to Thorne-Zytkow objects. I'll step through the most interesting ones that came out of that meeting here. So the first question is HV 2112 actually a Thorne-Zytkow object? This star has been brilliantly poked and prodded since we first published that we thought we'd found a TZO in 2014. So far, it stood up to scrutiny, but we've learned a lot of really useful things by questioning, what is this star really? The first question that it actually came up was, is it in the SMC? And standing here now, that sounds like a really dated question, but in 2014, that was not that obvious. There was a paper put out where the authors actually looked at old astrometric data of HV 2112 in the SMC and were pointing out, you know, there's one outlier in this data. Its proper motion might not be exactly right for the SMC. It could be a very unfortunately similar moving halo giant in the Milky Way. If it's a halo giant, it could be polluted by a white dwarf companion or by a previous supernova. You could explain those abundances in other ways. It would obviously be much dimmer. We don't think this is in the SMC. We don't think it's a Thorne-Zytkow object. This finally got resolved when the Gaia data release came out in 2018. What had actually happened was the authors of the paper showing sort of the Gaia data that you see here got the data release and started tweeting, we are going to check on some stars to see where they are. Does anybody have a favorite? And someone said, check on HV 2112. And they started live tweeting. We're downloading the data. We've figured out a distance of this. I was boarding an airplane at the time and walking down the jetway, refreshing Twitter, going, is it in the SMC? And the good news is it is. It has now definitively been proven that it is in the SMC, which makes its luminosity very interesting. It's clearly a very luminous red star. We are now looking at whether or not it is luminous enough to be a red supergiant or a red supergiant-like star. And the answer is yes, it's luminous enough. Anna O'Grady, who up until recently, she just defended her thesis at the University of Toronto, has actually been looking at HV 2112 and other stars like it for years, because it's right on the line of whether you could call something a red supergiant as opposed to a super AGB star, so a red giant that's just gotten excessively massive. And again, this matters because how you interpret the abundances changes. If this is a super AGB star, you can explain at least some of the element abundances in other ways. The remaining ones can be explained away if you add in a companion or some other source of pollution. What Anna ultimately concluded was that HV 2112 isn't really quite like a normal red supergiant, but it's not like other super AGB stars either. She put out a paper just this year where she described that if it was an SAGB star, it would have to be maximally massive. It could be considered an AGB star, but it would redefine the upper limit of what AGB stars are, which is a dangerous thing to do with a star that I think is this strange. So we're now fairly certain that it is red supergiant-like enough that it could be considered to be a supergiant TZO. We're also trying to look at whether something else can explain its various odd behaviors, whether we can explain its emission features by it being an AGB star like Myra. It doesn't look like it. It looks like it's too luminous. Can we throw in other explanations for the weird chemical abundances that we're seeing? Possibly, but the explanations start to become overwrought enough that having it be a TZO is bizarrely the simplest explanation, as opposed to a binary that was also polluted by something else and may have an excess of so-and-so. A TZO winds up being the most elegant explanation. Beyond HV 2112, we're also trying to answer a bunch of questions about how to make TZOs, how to search for them, and how long they live and then how they die. So to start, we can talk about what the progenitors of TZOs are. We know that they likely originate from binary systems, or at the very least from two stars separately that may or may not be in a binary. I promised we would come back to this later, so here we are. There are a lot of questions about how exactly those two stars should look before they merge to make a TZO. This classical picture that I imagined, where you start with two blue supergiants in a binary, one dies, leaves behind a neutron star, and the other expands to become a red supergiant, has long been the most traditional picture of how to make a TZO. But there are a couple catches with this. For one, what a high mass X-ray binary looks like when it has a red supergiant for a donor star is very unclear. I'll talk more about that in a moment. This is also not the only way to stick two stars together to make a TZO. This is the sort of classical picture of an engulfed neutron star. You have a neutron star and red supergiant in a binary. The red supergiant overflows its Roche lobe. Because this is the biggest state of a star, this is the easiest way to do it. Captures the neutron star, it spirals in, and the magic step that I talked about before happens. You could also do this in another way, though. You could have, for example, a red supergiant with a binary companion that dies and forms a supernova, and then gains a kick from the supernova. The kicked neutron star could then, in principle, get flung right into the red supergiant. So it's a supernova with really perfect aim. If that happens, then you wind up with a neutron star and a red supergiant colliding, and based on the nature of the collision, you might punch the neutron star straight through the outer layers of the red supergiant. They could merge very directly and very violently, or you could wind up with something in the middle where the red supergiant does spiral in, disrupt the core, and wind up forming a TZO. You could even do this in a third scenario where the two stars aren't in a binary and you just wind up with good old-fashioned dynamical capture. That's pretty hard to do for massive stars just because they are not that dense in the universe unless you get into the very densest of a massive cluster, but it's not impossible. Physically, though, you can model it in just the same way of two stars in a binary that were not close to merging, where one star, the neutron star in this case, then experiences a kick. So this winds up introducing a few slightly unusual questions. We have, like I said, this question of what the donor star of a high-mass X-ray binary looks like when it's a red supergiant. We have only a tiny handful of X-ray binaries that have ever been observed where we think that the donor stars are red supergiants. There was one discovered completely serendipitously by a group looking at M-dwarfs years ago. Amanda Gottlieb found one a few years ago near the Galactic Center. I believe there has just been one more. I don't off the top of my head remember the authors, but the sample is in the, count on one hand side. There's some arguments that ultraluminous X-ray sources, so ULXs, could have red supergiant donor stars. These have been studied in the infrared. It's actually surprisingly hard right now to definitively type a star in the infrared and prove that it is a red supergiant as opposed to some other cool or luminous type of star. But knowing how common these systems are would be very useful if we're simply trying to figure out how many Thorne-Zytkow object progenitors exist that could make one. This gets even more complicated because the star that is merged with, the star that consumes the neutron star, does not necessarily have to be, as it turns out, a red supergiant. You could start with a main sequence massive star, or even a main sequence close to massive star, something like 5 solar masses and up. When that star consumes a neutron star, the act of the merger could actually puff up and inflate the star such that the end product looks like a red supergiant, even though it didn't look like a red supergiant initially. This is actually an interesting thing that a student of mine at the University of Washington is modeling right now, and I mean, what time is it there? 3 a.m.? No. So not literally right now, but close to right now, we are running these models. I got this very preliminary video from her this morning. I've watched it twice. so we can all watch it together this third time, looking at trying to model the merger of a main sequence massive star and a neutron star. So she's doing the modeling using MaNGA, which is a moving mesh hydrodynamic solver. We have a 5 solar mass main sequence star here. The little x is currently just being treated as a dark matter particle, but dynamically that is what we're treating as our neutron star. And we're plotting in color, you see the projected density of the environment getting plotted. What we're imagining here is that second scenario that I talked about, where the neutron star has been flung at the in this case, main sequence star. And it's being flung right now with a periastron, so a closest pass radius of just 1.25, so just slightly bigger than the radius of the star itself. And you can watch what it does. So it starts off by immediately disrupting and then puffing up that envelope. So you wind up with a big and lower density envelope. The neutron star looks like it might make it. It looks like it almost might get away. It has been gravitationally captured. You see it heading toward the core, and then the core winds up merging. You can now start to watch what the outer layers of the star are doing. We have not even opened up the actual numbers from the results of this animation. We've just gotten the chance to look at this, but you can tell just at a glance that the outer layers of this star and the surroundings of this star look very different than they did before it merged. It certainly no longer looks like a main sequence star. It's going to be something much colder. We need to understand what sort of opacities we're looking at, how this would actually look to an observer. But this is an example of the types of models that Lauren is running. She has actually run a bunch of these for 5, 8, 12, 15, and 20 solar mass stars. In a lot of these cases, the neutron star simply flies away. In many of these cases, she's emailed us saying, I killed the star. When we actually merged, everything just died. But in more than one case, we actually have at least a handful of cases where the cores successfully merge and the star survives and the star is able to support that envelope. So we are making TZOs with these models. What they actually look like to an observer, how long they live, are all still open questions, but it's starting to poke and prod at the idea of forming one of these and actually having it survive and make the star that Kip and Anna predicted. Another interesting detail of all of this is the timing, because you don't necessarily have to have a red supergiant that is merging with a neutron star, but you do have to hit a massive star at a certain point in its evolution. Even the idea of the two stars in a binary becomes a bit complicated because you need the binary's primary to die and make a neutron star and for the secondary to survive long enough for this merger to happen. If the mass ratio is too close, both stars will die and you wind up with a compact object binary. If the mass ratio is too far apart, one star will have died and made a neutron star before the other star has even finished forming or when it's barely left the main sequence. And trying to pin this down actually gets into really interesting questions about modeling binary evolution, period. Something as simple as deciding when the two members of a binary are considered born, when they arrive on the main sequence and when they start fusing hydrogen, can make a huge difference. This doesn't matter for most binary models because the differences are small. You're talking about the pre-main sequence lifetime. You're talking about differences of 10,000, 100,000, maybe at most a million years. And for most binary evolution, that's fairly minor. But if you're dealing with the exact timing of when a binary merges, something that minor starts to make a big difference. So we're starting to look at this on a sort of large-scale binary modeling scenario to see if building in delays in their birth or other details of timing once one member has left the main sequence, to see if all of that could start affecting exactly how you could hit the sweet spot of making a Thorne-Zytkow object. So I've listed off a bunch of things that we don't know about the progenitors of TZOs. Most of these tie into things that we don't know about massive binary evolution. It's all really interesting for studying TZOs. It's also really interesting because there are other reasons that we are interested in massive binaries. We've seen an explosion, literally, of interest in massive star mergers in the past few years because of gravitational waves and because of the neutron star merger that was detected back in 2017. We really need to understand what population of massive star binaries lead to compact object binaries, because this directly tells us how many neutron star mergers or neutron star black hole mergers we would expect. If an alternate evolutionary channel for these binaries is making a TZO instead, I think a gravitational wave person would describe a TZO as a failed compact object merger. It's a merger that happened a little too soon. From our perspective, the compact object mergers are the TZOs that waited a little too long. But they're a different part of this same landscape, so understanding if TZOs even exist, how many of them are there, and how they're made, all of that winds up making a big difference when you try to imagine the population of compact object mergers. So speaking of gravitational waves, another question that came up at this meeting was what the observational signatures are of TZOs. I already talked about the strange abundances that you can look for. But again, you can explain atmosphere abundances through a bunch of different things. If you tweak a little bit of a star's nucleosynthesis, if you add any pollution from a companion or a nearby supernova, you can quickly start turning the dials and slightly adjusting the abundances you would expect to see. And the abundance enhancements that we see, at least in HV 2112, are subtle. Ideally, we would like some other tests of whether something is or is not truly a Thorne-Zytkow object. The figure on the left is from Anna O'Grady's 2020 paper, where again, she was looking at HV 2112 and other stars like it to determine whether or not it is supergiant-like or more like a super AGB star. And this is the light curve of HV 2112. I know it's small on the screen, but its full amplitude spans 4 magnitudes. Even in the Harvard Variable Catalog, it's one of the most variable stars in the whole list. You can also see, if you look very closely, that the light curve has this distinctive sort of double bump feature. It brightens, drops, brightens again, and drops off. We think this double bump got lost just due to an observational gap, and then once again, it brightens, dims a little bit, and brightens again. This is a signature associated, again, with Myras. It was a very useful piece of information in trying to figure out whether HV 2112 is just an unusually bright Myra. It doesn't appear that it is, but it appears to be undergoing similar pulsations. So looking for other red supergiant-like stars that have this type of signature in their light curve could be a way of identifying TZOs. Again, though, it's sort of circumstantial. You could just explain it by some other oddity of the star. What we would really like is some unambiguous sign that you have a cool star with a neutron star in the center. And that is where the idea of gravitational waves comes in. Because once a TZO has formed, you have a likely very rapidly rotating neutron star sitting at the heart of an envelope and slowly accreting material from that envelope. That neutron star is going to be spun down over the course of its lifetime inside a TZO, and it is going to be slightly asymmetric along the rotation axis because of that accretion. So what you should have is the thought experiment of a neutron star with a mountain on it that is slowly spinning slower and slower. So it should be emitting gravitational waves. It should be emitting a continuous gravitational wave signature, which is great from a gravitational wave standpoint, because so far we have only found transient gravitational waves. The gravitational wave signature appears, it disappears, and we're left to go, oh my God, where was it? And in the case of a neutron star merger, if we're lucky, try to look for the electromagnetic counterpart. With the continuous gravitational wave signal, we can take our time. A student of mine, Lindsay DeMarkey, wound up modeling what the continuous gravitational wave signal of a central neutron star should look like in a TZO. The plot is fairly straightforward. It's just a red line right here at the strain where you would expect to see the neutron star at the center of a Thorne-Zytkow object. The black curve here is the advanced LIGO design noise curve. But what we'd seen was that this should be detectable with advanced LIGO if you can take a coherence time of several days. And since it's a continuous signal, we can do that. We can just take, in this case, 5 days of advanced LIGO data in a region like the Milky Way's center, where we know there are heaps of red supergiants, clusters with red supergiants and coeval neutron stars. This is the best place where you could possibly make a TZO. We could just effectively stare at that part of the sky with advanced LIGO for something like 5 days and look to see if a continuous gravitational wave signal leaps out at us. We can then run after that signal with a telescope and see if there is a red supergiant sitting there. Another perk of staring at something with 5 days worth of advanced LIGO time is those giant location bananas that you've seen on pictures of gravitational wave transients shrink dramatically. So we should eventually be able to pinpoint exactly where the continuous signal is coming from and see if a red supergiant is there. So if you see a big cold red star that is emitting continuous gravitational waves, that is the smoking gun that there is a neutron star at its core. This is very difficult to do. We're now working on getting permission or going through the process with LIGO of getting access to that data. And we don't have any Thorne-Zytkow object candidates that we specifically want to focus on in the galactic center. We can observe lots of red supergiants there, but because of the dust, we're observing them in the infrared. We don't know nearly as much about red supergiant infrared spectra, let alone a shell infrared spectra where we could identify the lines that would tell us something might be a TZO. So it's very much a preliminary idea, but it does at least give us a recipe in principle for how to definitively detect a TZO. We can't do this, sadly, at the distances of the SMC, at least not with advanced LIGO, and by the time you go to LISA, the strains are actually too low, we think. This strain was modeled taking a particular breaking index for a neutron star. We had to pick some sort of picture of the equation of state of a neutron star. Obviously, changing any of these things could change the strain, and perhaps it is eventually doable with LISA. There's a lot of question marks there, but we at least have the start of an idea. Now, the very last thing I want to touch on, because I know we're getting to the end of our time, is the lifetimes and end states of Thorne-Zytkow objects. We do not know how long TZOs live, and we get two very different answers depending on which mechanism we model for dictating their lives. Traditionally, a massive star would die because it runs out of fuel in its core fusion ends, the core collapses, you get a supernova, the end. In a Thorne-Zytkow object, this is not necessarily the case. That neutron star core could sit at the center of that envelope, very, very slowly accreting material for an incredibly long time. So you could have a Thorne-Zytkow object that lives for billions of years. And this should be an interesting observational smoking gun to look for, because what you would see is a red supergiant lurking in a globular cluster, a star that is apparently far too luminous and far too massive for the environment that it's in, because it's lived an astonishingly long time. We actually thought we might have found one of these. It now looks like that might be a great example of a super AGB star, although we're still playing with it. But this could be an interesting sign of a TZO if it has lived an extraordinarily long time. However, you could have a completely different mechanism dictating how long a TZO lives. They have these big, cold, puffy, extended envelopes. Because of that, they're very strongly mass losing. I mentioned this at the beginning. If they are shedding mass, especially if they are pulsating and puffing off huge amounts of those envelopes, they could live a relatively short amount of time. They could live on the order of 100,000 years because that envelope eventually gets shed, and what is left behind is a slowly rotating neutron star. Again, this is actually something that someone observed. Back in 2015, there was a paper looking at a slowly rotating neutron star that was described as potentially the result of a TZO that had lost its envelope. We have no idea which one of these is true. Trying to model this is incredibly complicated. As a not really a theorist, I leave it to the theorist experts to tell us just how impossible it is to distinguish between these two scenarios. I'm seeing looks like really impossible. But knowing this has a huge implication for how you look for a TZO and the implications for how many there are. Out of a sample of several thousand red supergiants in the Milky Way, how many of them do we expect to be TZOs? Out of the TZOs in the SMC, how many do we expect to be there? Old estimates looking mainly at the mass loss-driven lifetime looking mainly at the neutron star core-driven lifetime had expected that something like 1 in 100 red supergiants could be a TZO. We searched about 100 red supergiants when we went to Magellan, and we found one TZO. So in the astronomy world of statistics, that's perfect. But we'd ideally like to know a little bit more about how many there are and what that means for where we should be looking and how hard we have to look. We also don't know what the terminal product of a TZO is. Like I said, you could puff off the envelope and leave behind a slowly rotating neutron star. You could also imagine a scenario where that neutron star, especially if it started off close to its maximum mass, does eventually accrete too much material and collapse into a black hole. In a scenario like that, you could wind up with a TZO that disappears via direct collapse. And we have observations of this in NGC 6946. I know that there was a group that saw the disappearing red supergiant that they described as a potential direct collapse supernova. You could see something like that with a TZO. The core becomes a black hole and the star just disappears. There also could be some sort of supernova-like explosion. This has been modeled in the past couple of years. It's a little hard to picture because when you lose the neutron star, you don't necessarily have anything for the shock to bounce off of, but you could wind up with a explosion-like or transient-like event that would be the smoking gun of a TZO dying. In addition to understanding this for the purposes of lifetimes, it would also be good to know what these terminal products are, period, especially because if they're any sort of electromagnetic transient, we're about to get incredibly good at finding these. When the Rubin Observatory turns on, if it starts detecting direct collapse red supergiants, stars that are just suddenly disappearing, it would be great to know how many of these are regular red supergiants and how many of these might be TZOs. If we can get a population statistics level understanding of these, that could be another way of testing whether TZOs exist and how many there are. And then finally, I've said this over and over again throughout the talk, do TZOs even exist? This model is still getting poked and prodded, and by this model I mean the original picture that Kip and Anna put together of a neutron star supporting an envelope. I am sure most, if not all of you, are sitting there going, well, what if the neutron star just quickly accretes too much material and dies? How can it stably sit there in the core and not destroy the envelope or immediately destroy itself? This is not an area in which I have a great deal of expertise, but I know that there is a debate going on about how easily this can happen, whether TZOs form and live a fraction of a second, or whether they live billions of years. Knowing this would be incredibly useful for understanding stellar interiors and for understanding TZOs themselves. Even if it turns out that TZOs can't exist, all of the questions that we're asking here about binary evolution, the observable signatures of these stars, how to look for continuous gravitational waves, the different terminal products and how to look for them as transients. All of these are really interesting for massive star post-main sequence evolution in general, binary evolution in general. If we explore TZOs and don't find anything, or we find that TZOs don't exist, we'll still have learned a lot about massive stars along the way. So either way, it's an exciting project to be exploring. It's something I've started during this past year on my sabbatical in earnest, and something I'm looking forward to working on over the next few years. So on that note, I'll leave these many current questions up, and I'm happy to take any questions. Thank you.
Thanks a lot, Emily, for a very fascinating talk. Questions? All right, we'll start from the back and we'll move toward the front. Huh? Yeah, so let's start there and then go here. Okay, yes.
Okay, thank you for the very interesting talk. It's the first time I've heard about these objects, and I can think of many questions, but I'll stick to my area of expertise, which is mostly gravitational waves. So you've shown that these objects might be detectable by the continuous gravitational waves that would exist. I know from some earlier research that at least for neutron stars on their own, given the very near spherical shape they would expect to have, that at least for advanced LIGO and the current generation of detectors, we don't expect to see them. But next generation, so Einstein telescope and Cosmic Explorer, given the rotation rate is in that frequency range, they would be detectable. Do you think that we would be able to distinguish this from a neutron star with a mountain?
It's a good question. I think the only way, I think the only confident way we could do it would be to do electromagnetic follow-up. Okay. And if there's a red supergiant there, it's not a neutron star. There might be subtle differences in what the breaking index is and how it's spun down, that a neutron star spinning down just on its own, as opposed to a neutron star spinning down with an envelope on it, would have, like, you would expect perhaps the frequency of the signal to change at a different rate. Yeah. I'm guessing we know so little about neutron stars and about spin down that we would basically be able to say, this one's weird, this one is also weird. Are they differently weird from each other in the right way? I think we would need a big sample before we could say anything about it. So I think E&M follow-up is the best way for now.
Okay. Yeah, no, that's also where we know these candidate neutron stars, well, that they exist at least, right?
Yeah.
Because we haven't detected anything. And I think that the ground-based detectors are more likely to find these kind of objects compared to LISA because of the frequency band in which they observe the spectrum. Thank you.
Thank you.
Probably a more detailed question on the binary evolution. It seems to me that you have a bit of a timescale problem.
Yes.
Because you show two blue supergiants, which means that you have to start with an incredibly wide period to make sure that they don't interact at all.
Yep.
And then you want to merge them. So any ideas on how you lose all that angular momentum? Because you start with a binary, well, two blue supergiants, so say few hundred days minimally.
Yeah.
And then you merge them, which means that you have to get them to a period of less than a day.
I think that, so there's two different ways to solve that problem, and I think one is that you don't assume that they don't interact. I've been working with Jan Eldridge's group and the BPAS models on this, and there is a whole set of TZO progenitors, I don't know, like one of the earlier steps that you could make if you had interaction when the stars were in an earlier state. You could turn the primary or you could turn the secondary into the more massive star, you could exchange mass, you could circularize the orbit, and you could still wind up with something that could make a TZO. It's easiest to imagine them not interacting, but earlier interaction doesn't prevent a TZO from potentially forming. Or you imagine the second scenario where there is a supernova kick or similar, where you force them closer together. And that isn't actually as strange as it sounds, because if the binary is already, I know a few hundred days is wide, but if it's already close-ish, and especially if the secondary is already a red supergiant and subtending a pretty big angle, the aim doesn't have to be that perfect. This is why Lauren in her models is looking at different sort of radii of closest approach, because you could aim directly for the heart of the star, you could aim for a glancing blow at the edge of the star, you could aim for even further away and see what happens to the captor. So that can also solve the problem. The timing actually comes more from the evolutionary states of the stars, that you could imagine an equal mass binary, and then you're sort of okay, but they're going to die very quickly. If you wind up with binaries of sufficiently different mass, you wind up with this very strange problem where the more massive star has died while the lower mass star is still forming. And I am not a star formation expert at all. I've started to build quite a list of questions for star formation experts on what a low mass forming star's life is like next to a O star blasting it with UV radiation, because it really starts messing with the timeline of what that binary is going to look like. So we definitely have a timing problem. We can fix the exactly when it merges problem with a kick or similar. In terms of the timing of the binary's evolution, that's actually getting pretty messy. It's certainly solvable, but it opens up bigger questions about binary evolution, period.
Thank you. That was a good answer. Thank you.
Okay, we had here as well on the front row.
Hi, and nice talk. My question to you is basically, whatever happened to the rest of those weird transients? Because you were originally tipped off by these weird Hayashi cheating stars, right? You found one TZO maybe. So it's also not really clear to me how being a TZO allows you to cheat this metallicity dependent limit also. So if you could explain that, that'd be great. But what about the rest of them?
Yeah, we don't know. We still can't. So interestingly, the star that we found that was a TZO candidate was not one of the original weird spectroscopic variables that we'd found. Had we observed this star at low resolution before we'd gone after it with the Echelle, we would have classified it as one. So it looks similar, but it doesn't behave like the others. If we did go and look at all of our weird spectroscopic variables, none of them have the abundances of a TZO. We think that what's happening is that as a group, when they are warmer, they are also brighter, dustier, and they are more luminous. So we think what is happening is that these stars are undergoing sort of periodic shudders, not periodic, episodic shudders of mass loss. And as they shed that mass, it obviously takes time for the opacity of it to decrease, for it to turn from gas into dust. And what we are seeing is effectively a false surface to the star. It appears to get warmer and then cool off again on a timescale of months, which is way too fast for it to be a true change in the temperature of the star. So it seems to be something not entirely different than the Great Dimming of Betelgeuse, but just with a different observational effect. We have 4 of them. And time domain spectroscopy, heartbreakingly, really isn't a thing yet. I would love to just get a spectrum a month of these stars for the next 10 years, and then we'd have a much better answer for you and hopefully find more of them. But that's our best picture of it for now, because it's happening so fast that it probably can't. It can't be a real physical change. It's something to do with its mass loss and the observational limitations of how we're looking at it.
Okay, just quick bonus question.
Yeah.
HZ2112, outside or inside of the SMC or LMC, whichever one it was?
It's in the SMC.
So on the interior though, not like just on the outside.
Actually, it is closer to the outskirts. There's other red supergiants like that, but if you were to place it on the SMC and then map the other red supergiants, it looks a little lonely, is probably the best explanation it can give. I don't easily have a image I can pull up with a little X where it is, but it's not in the heart of the SMC. It is not so far in the outskirts that it's in the stellar stream or something like that, but it's not in the densest part of the SMC.
Okay. But not far out enough to be really weird to have such an exotic massive binary.
I don't think so, no.
multiples in. Okay.
No. We found it to add to our list based on a list of sort of massive star, a list of, massive stars or red supergiant candidates that Phil Massey had. We actually added the star to our list almost at the last minute. His list wouldn't have extended to the outskirts where massive stars would be weird. Yeah.
Hey, great talk. I was curious about, you mentioned that the fine-tuning for the stars, the initial conditions for the binaries to get to these points where they form a TZO are very fine-tuned. You need certain mass ratios, the premium sequence lifetime is very uncertain. But in population models, we see lots of failed common envelopes, mergers with neutron stars. Why would any of those not be a TZO candidate?
I don't know. They could be. I think I do remember talking to someone about this and them saying something like, oh, we make these all the time. And the answer being, I think that's bad, actually, because we don't actually think that there are heaps and heaps of TZOs. If we really made them all the time, we'd have vastly more red supergiants in a stellar population than we would expect. We'd have this problem of why do we have so many excessive cool luminous stars that we can't explain, and that doesn't appear to observationally be the case. There are other ways that they could fail. The merger of the core and the neutron star could kill one or both of them. You could have a merger where the envelope is immediately dispelled, so you don't wind up with something behind it to be supported. It gets into details of common envelope modeling that I'm not an expert at. Lauren is, and her other advisor on this project, Phil Chang at Wisconsin, also knows a lot more about common envelope mergers and modeling than I do. So I think that most of the failure modes come from what actually happens to that material during the merger itself. Maybe there are more than we think. That would be great.
Would you be able to use follow-up observations of LRN to look for potential TZOs?
Of LRN?
Sorry, luminous red novae, merger candidates.
Maybe. I think the interesting thing there is that those would be brand new, newborn TZOs, and a topic that I've really never seen covered in the literature in any detail is how long it takes those IRP abundance, like oddities, to build up at the surface. A TZO that was born yesterday, I don't think that we could identify, because I don't think you would have that buildup of excess molybdenum or excess lithium at the surface. Maybe it happens pretty fast. You do have very fast convection speeds in the envelopes, but maybe if we went back and followed them up in a year, maybe if we followed them up later, we could find something. Or maybe if we just did an immediate follow-up and said, hey, there is a red supergiant-like object there. Maybe once we get the better gravitational wave detectors, we can immediately see signs of a continuous gravitational wave. Maybe that would be a way to do it, but just imaging by itself or just spectroscopy while the TZO is really young, I don't think would be enough. Maybe we could try. It sounds like a cool idea.
Thank you.
Yeah. There's.
Okay.
Thanks for the very nice talk and introducing us to these TZOs. My question is more on the nucleosynthesis side. For example, S-process, theoretically, S-process efficiency has a strong dependence on metallicity, right? Because you just have more neutron exposure for less low metallicity stars. So do you have such an idea for the IRP process? Because maybe that can be a distinguishing factor between the S-process and IRP process.
I have not
abundances.
I have not seen that yet.
Okay.
There was a paper just a few months ago by Rob Farmer and his group that was looking at simulating a TZO and then simulating abundances from it. They had to tackle the same difficulty of everyone else of you can't model a neutron star. So what they did to model the neutron star unfortunately really messes with how the IRP process could work, because they were imagining a very big radius. It changes the size of the envelope. It changes what that would look like. But there's at least work going on this, and they might have considered metallicity. I know that the original paper didn't, I don't believe, played with it enough that we could say something like what's going on in the SMC. I do think that sort of thing could be a good distinction. Another problem we ran into in 2014 is that at the time, we weren't even measuring abundances because we didn't have a good way to simulate an entire red supergiant atmosphere. We still don't really, but we're getting better at it. So we couldn't easily simulate an entire red supergiant atmosphere and then just say, turn the molybdenum all the way up. And we're getting better at that now. So hopefully in the next round of observations, I have another student at UW who actually has observations of HV 2112 coming up in a month on GHOST, which is a brand new Echelle spectrograph on Gemini. We're using the shared risk time to point at it, And with that, she might be able to get actual abundances of like ruthenium, which we haven't looked at before because we're specifically focusing on the blue. So we might get there. And then it should be obvious what the difference between the S process and the IRP process is. I still think we'd want to do it with multiple elements, though. I think if you just found rubidium, there was a paper published IDing another potential TZO candidate, but they were only using the rubidium line. I don't think, even if it looks different than the S process, but like different but not too different, I don't think that's enough on its own. I think we need a suite of elements.
All right.
Yeah.
Thank you.
Some more questions in the back.
Thanks, Emily, for the wonderful talk. So you constantly compare these stars with mirrors. And when I look at the light curve, it also looks very similar. The time scale is similar. What makes you believe these objects are not mirrors? Is this like an abundance part and luminosity, whatever?
It's a good question. And I think the answer depends on what side of stellar astronomy you're coming from, because the bad answer is they're not Miras because Miras are giants and these stars are supergiants. Obviously, this is not a good answer because you could have the same mechanism that leads to those Mira-like variations just in a supergiant. I think the thing that mostly catches our attention is that for a supergiant, for a very luminous massive star, this is pretty much the only example of a light curve like that we've seen. We haven't seen normal red supergiants that behave like that. So the Mira mechanism that is not uncommon in red giants doesn't appear to show up in red supergiants except for this one. Maybe there is a whole class of supergiant Miras or supergiant stars with Mira-like pulsations, or maybe whatever this star is, something is causing that. But right now we're distinguishing based on pretty much luminosity class and presumed mass. But there's certainly no reason to think that you couldn't wind up with that behavior at that mass. It's just something we have not seen aside from this one very weird star.
Yeah, thanks. And one more quick question. The optical spectra are extremely complex, but these are also red stars. Have anyone looked at those in the near infrared or far infrared?
The optical spectra?
No, so the near infrared spectra, can they teach you something in addition to the optical spectra?
I'm sure they can, and I very badly want to look at these in the near infrared, mid infrared, far infrared. There are now infrared shells that we could look at. Even at lower resolution, these stars could be really informative in the near IR. And this actually gets back to a really interesting observational problem with red supergiants as a whole, that they are shockingly understudied in the near IR. Their spectra peak at about 9,000 angstroms, so they are as bright in the J band as they are in R and I. But we have surprisingly little in terms of observations of them. The red supergiants that we know best and like to observe tend to be fairly bright, and we don't put IR spectra on little telescopes. So, for example, we don't have a nice near IR spectrum of Betelgeuse because there's no telescope small enough to point at it with a good IR spectrograph. I actually have a proposal in right now to try and use JWST to take the world's shortest JWST exposures and try to start building up a library of near-infrared spectra of red supergiants. We also have some observations still sitting on a hard drive that need to be finished of red supergiants with SOFIA, where we could get at the mid-IR. As you get to longer wavelengths, there's a point at which you're no longer looking at the surface, you're looking at the dust, but that's informative in its own way. Even in the near-IR, there's some lines that are potentially useful. I'm trying to look for sort of the near IR equivalent to the titanium oxide band so we can measure temperatures easily. There's some atomic lines that other groups have used that are famously insensitive to temperature, but you can use them to measure metallicity. It's just still really understudied. So I would love to point at this star in particular and red supergiants in general with a near IR spectrograph, and it's just a matter of finding the spectrograph, getting the time, and then being able to interpret what we did find.
Well, there is at least one, such a spectrograph. That's apogee.
Mm-hmm.
Right?
Yeah.
I don't know if these stars would be bright enough for it, with a limit of like 12.5 in H band.
I mean, you could certainly do it in the Milky Way. And another challenge is that the lines, for example, that I'm interested in as temperature gauges are further in the red. They're out at like 4 or 5 microns, so you do start struggling with what you can do from the ground. But yeah, it would be really great to actually get at these stars in the near IR.
All right. I think that, well, it's almost time for lunch, huh? So we're going to thank Emily again for a wonderful presentation. So she's going to be around during the afternoon until she moves on her Euro tour. So if you would like to chat a little bit more in detail about something with Emily, then just come up now and let me know, and we'll schedule it in. Otherwise, you can also just come by. We'll after lunch, we'll probably hang out somewhere around my office in there. Okay, thanks.